This edition of the Bio Report is brought to you by the California Technology Council, providing discounts on products and services essential to every startup. For more information, visit californiatechnology.org/member benefits. I'm Daniel Levine, and this is the Bio Report. The growing promise to harness biology to address environmental, agricultural, health, and energy needs is fueling a new bioeconomy. The state of engineering biology will be on display at the SynBioBeta SF 2016 conference in South San Francisco, October 4th through October 6th. We spoke to John Cumbers, founder of SynBioBeta, about the state of the industry, the challenges it faces, and the long-term potential it holds for transforming our manufacturing sector. John, thanks for joining us.
Absolutely. Thanks for having me.
We're going to talk about synthetic biology, the upcoming SynBioBeta conference in San Francisco, but perhaps you can begin with an issue of terminology. In broad terms, what is synthetic biology?
In broad terms, synthetic biology is making biology easier to engineer.
There seems to be a lack of agreement on the terms used to describe this. I've seen that within government agencies in particular. There's not an agreement on how to describe what they're doing. There's a fair bit of mistrust and a lack of understanding on the part of the public about this area. Does this emerging industry need to be sensitive to issues of terminology, and is there a need to reach some kind of common agreement on the terms used to describe what it does?
There was a paper in Nature, an editorial in Nature, where they asked a number of different experts on the definition of synthetic biology, and I think they asked about 14 different scientists and engineers, and they got 14 different answers on what it is. Which was better. It could have been 15, right? But I think that the most important thing is to focus on the outcomes of what this technology can do rather than needing to give the technology a name. And the outcome of what this technology can do is make new things sustainably, use CO2 as a feedstock instead of oil, make new flavors, fragrances, building materials, fabrics, using all the elements that nature's given us, and all the tools of biotechnology over the last 40 years to help us make it in a better way. Better could be less toxic for the environment. It could be more sustainable using fewer resources, or it could be better products that are functioning in a higher performance way than we have had them do in the past. I think the terminology analogy that's good to think about is the term Web 2.0. What was Web 2.0? Well, you could go back 15 years to the birth of the Web 2.0 movement, which was after the dot-com bust, and you can see this upswelling of new companies, new entrepreneurs, new ideas, and new investors who are backing those crazy entrepreneurs with these new ideas. On the surface, it kind of looked a little superficial. It looked like shiny new logos and funky web domains. And there were a lot of people at the time that said, what is this Web 2.0? I've been doing, web for the last 10 years, and this is nothing new. It's just superficial. A rebranding, its hype, its buzzwords on top of what we've been doing all along. But what's come out of that whole Web 2.0 movement is amazing new tools and technologies to run the web, and amazing new companies that are now worth billions of dollars. Just look at Facebook across the bay in Menlo Park to see one of the best examples of it. I think the same is similar for synthetic biology. If you look at what are the core technologies, there's sequencing, there's synthesis, and there's the abstraction of engineering principles onto the design and construction of biological systems. So those three things have been around since the 1970s. Fred Sanger was the first person to write a base pair of DNA in the 70s, and then a couple of years after, he was the first person to read a base pair of DNA as well. We've been trying to apply engineering to biology for the last 40 years, ever since the discovery of a restriction enzyme that cut a piece of DNA in a specific place. But the reality is that we're fairly useless at engineering biology. It's still a very laborious process. It's still a very manual process, still a very time-intensive and resource-intensive process to do anything in biology. What this synthetic biology movement has brought about is almost a rallying cry to the next generation of entrepreneurs and scientists and engineers to say just because biology is hard to engineer doesn't mean it always has to be hard to engineer. And you're seeing a lot of people enter the field of biotechnology, of genetic engineering, and they're coming into it from fields like software engineering, computer science, electrical engineering, civil engineering, materials engineering, mathematics, physics, a lot of these engineering disciplines, and they're coming in and they're saying, how can we apply these principles of engineering to the design and construction of new biological systems? Now, is there a certain amount of hype around the term synthetic biology? Sure. Is there a certain amount of rebranding around the term synthetic biology and away from the term GMO, which has a lot of negative connotations? Sure, there is. Is there a certain sense that this is the same thing that we've been doing for the last 40 years in terms of genetic engineering or bioprocess engineering or industrial microbiology or industrial biotechnology? Sure, there's commonality between all of these different disciplines. But then going back again to the Web 2.0 analogy, if somebody came to you now and you asked them, what do you do? And they said, I've got a Web 2.0 company, you kind of laugh at them. They're like, well, what is Web 2.0? It was something 15 years ago. I think the same will be for synthetic biology in 10 years' time. You won't use the term synthetic biology. It will just go back to genetic engineering or biological engineering. But I will place money that the Fortune 500 or even the Fortune 10 will have synthetic biology companies in it, just like we're seeing now with Facebook and Twitter and Google and Amazon, all in the top 10 companies on the Fortune 500 now. Maybe Twitter's not quite up there anymore, but certainly Amazon, Google, and Facebook are. So I think you're going to see a huge amount of great applications come out of the birth of this new industry. And there's definitely a certain sense of rebranding, but I think it's going to have a huge impact. And we're going to see that over the next 10 years and then over the next 50 years of how this technology is seen and how it's utilized and how we see it grow and start to get amazing products out there into the hands of consumers and really start to make a difference in terms of the kinds of applications that we're seeing biotechnology used for.
I want to go back to a point you touched on earlier. In your day job, you work with NASA to use synthetic biology to address some of the challenges with food, water, waste, and air we face in space. It's a fitting analogy to our own planet as we consider finite resources and the need to address global issues with food, water, waste, and air. What's the promise for harnessing biology to address those issues?
Well, that's a great question. And I worked at NASA for 7 years in the synthetic biology program. I was lead for the planetary sustainability initiative there. I actually left NASA just last year to go full-time at SynBioBeta, but I'm still very passionate about using these technologies in space. And I'm actually writing a book at the moment with Carl Schmieder from Messaging Lab, and the title of the book is What's Your Bio Strategy? And towards the end of the book, we're pulling out a couple of industries that we think are trillion-dollar industries that nobody's looking at. And one of those industries is the space industry. If you look at what's out there in space, in the places that are within a reasonable distance for us to travel to, they're within our solar system. And the places that have the best environment that we'd like to go are Mars or the Moon. Mars, because of the atmosphere that it has a 96-97% CO2 atmosphere. It has frozen water in its poles and all throughout the subsurface. And the Moon, not because of the atmosphere, the Moon has only a very, very, very thin atmosphere. But the Moon, because it's so close, but also because it has all of this water in the poles and in the subsurface. And I worked at NASA Ames in Silicon Valley, and NASA Ames had a mission about 7 years ago where they threw an empty fuel canister from a spacecraft into the South Pole of the Moon. And it threw up a huge amount of dirt and ice into the atmosphere. And that dirt and ice was looked at with a passing spacecraft. And they looked at it spectroscopically, and they analyzed what was in this big plume of dust that flew out from the South Pole of the Moon. And what they found was about 5.6% by mass water ice. They found a whole bunch of other things in there, including 0.04% by mass carbon-containing molecules. If you analyze the whole spectrum of what they found on the Moon, you find everything that life needs to survive. So sulfur, carbon, hydrogen, oxygen, nitrogen. And the one that they didn't find was phosphorus. But there is other sources of phosphorus in the lunar regolith, in the lunar soil. So based on that, we put together a paper that was published in the International Journal of Astrobiology that did a analysis on how you might use those lunar resources for the production of food. And we chose spirulina, a cyanobacterium that's grown here on Earth and sold as a health food supplement. It's a complete protein source. And we did a whole analysis for how you might go about farming the spirulina for food production on the Moon. And similarly, you could make the case for using biology to produce resources in space. Going back to what your question was, which was about using these technologies here on Earth and for sustainability purposes, we have no choice in space but to use sustainable manufacturing methods. We have nothing out there at the moment. So it's really important to try to develop these technologies that will recycle every drop of CO2, every drop of water, every molecule of CO2 that we might be respiring or perspiring as humans in space, and to build these closed-loop ecosystems so that we can both survive and thrive in space. One of the biggest problems of going into space is the cost of sending anything there. It's about $20,000 a kilogram to launch anything from the Earth into space. And using these technologies, we are able to recycle and close the loop on water, close the loop on food, and close the loop on CO2. So I think it offers huge potential for sustainability, both here on Earth and a huge trillion-dollar market for space as well.
As this industry started emerging, we saw a lot of early focus on biofuels because there were economic incentives to do that given the availability of subsidies. As gas prices fell and companies wrestled with the challenges of scaling up production, The shift is focused to specialty chemicals. If you think about where the technical challenges are today, where are they? Is it moving to commercial scale? Is it scientific? Is it economic?
I think that the science of scale is still the big one. It's okay and it's easy to get something going in a test tube in the lab on a small scale. But as soon as you start to scale up into larger and larger volumes, you start to see the impact of biology where it is surrounded by other cells, where it's surrounded by giant stirring tanks with heat and gas diffusion issues, with shearing issues of the walls of the tank. This is an unnatural environment for a lot of organisms to live in. Even if you look at organisms in the ocean, they're not as dense as they might be growing in a bioreactor. So the science of scale and the science of scaling and just manufacturing and biological manufacturing at scale, I think continues to be the Achilles heel of the industry. How do we take these things and actually scale them so that they are equivalent to a petrol refinery or a gasoline refinery or an oil refinery? So I think that is one of the biggest technical challenges. I think the second one is really how do we speed up the design, build, and test cycle for synthetic biology companies and synthetic biology systems. And if you look at the design, build, test cycle for any of these companies at the moment, it's probably on the order somewhere between 2 weeks and 6 months between them thinking of a concept and actually then having an organism that they've built to test whether it works or not. Imagine if your iPhone or your computer worked on that scale. If the developers at Facebook or Apple had to wait 2 weeks between the time they submitted their program to the time they saw whether it worked or not, we would be running, very slowly if everything took that long. Everything did take that long, of course. In the 60s, people were using punch cards to write programs on and to read programs and to store programs on pieces of paper, and then they literally would stack up the punch cards and then go back to the computer in a couple of days and pick up their results. So I think the industry is at the point where the tech industry was in the 1960s, and I think we're going to see huge advances in design, build, test, and in our ability to speed up the cycle so we can really make biology an engineering discipline that everybody's proud of.
One of the things you've noted in the past is that there's been a lot of attention on the revolution in our ability to read DNA, but there's also been a revolution in our ability to write it. What's happening in this area, and what's the significance of that?
That's right. Yeah, if you look at the Carlson's curves, which are named after economist and author Rob Carlson, which is like Moore's law for biology, and it shows that the cost of reading DNA and writing DNA is halving about every 18 months. So whilst the Human Genome Project in 2003 cost maybe 2001, cost I think over $1 billion, maybe $4 billion for a single genome. Now the cost of sequencing your whole genome is less than $1,000. Likewise, if you look at the organism that Craig Venter synthesized, Cynthia, the synthetic bacterial genome, when he did it, which I think was in maybe six or 7 years ago, I think the cost was easily over $1 million just for a single bacterial genome. And now the cost of that is halving every 18 months, and you can synthesize genes for about 5 cents per base pair at the moment. So any A, C, T, or G string that you want to write, approximately 5 to 10 cents per base pair. And there are a couple of next generation synthesis companies that have come online, most notably Gen 9 in Cambridge, and Twist Bioscience here in San Francisco. And they're both duking it out at the moment, lowering the price and increasing the speed and turnaround and the length of synthetic DNA. So it's a very hot market, and it's all great for the consumer because it means lower price of DNA, and the consumers can then think on a giga scale rather than a mega scale in terms of the gigabases rather than megabases in terms of how much they're going to synthesize. And there's actually a workshop that Gen 9 is doing at the conference called Gigabase is the New Megabase, teaching people how to start using and how to start thinking in these gigabase kind of order scales, which we've only really just started to see in the industry.
The 5th annual SynBioBeta SF conference will be held October 4th through October 6th at the South San Francisco Conference Center. What should people look for this year?
I think people should look for some of the new companies that we haven't heard about yet. There's an interesting one called Spira, which is making food using spirulina, the cyanobacterium. There are some interesting platform companies. Ginkgo Bioworks are going to be there from Boston. They just raised a $100 million Series C round, a huge amount of money for one of our companies in the industry to build out their new Bioworks platform. There's also a new platform company that you may not have heard of called Enevolve. And Enevolve has some really interesting technology that spun out of George Church's lab and Farron Isaac's work at Harvard. They're also based in Boston, and their platform is using a technique called MAGE, massively, I can't remember what the A is, massively something genome engineering. And it's a very interesting technique for using oligos to evolve a selected part of a genome. And they've also got some interesting technology around sensing metabolites in a growing bioreactor, so you can start to get some live readouts of some of the things that are happening inside the cell and inside the bioreactor.
As you think about the growth of this industry, where do you see it having the biggest impact, both in the near term and the long term? And do you ultimately see it transforming traditional manufacturing to more biologically based manufacturing?
I do. I really do see it transforming manufacturing. We did 3 events in China in June of this year, and there's a wonderful quote that I often use in my slides from Craig Venter, the founder of Synthetic Genomics, which is that over the next 30 years, everything is going to be made by synthetic genomics. And I think that's a really powerful quote, and it really looks at our petro-based economy right now and how we're making things and how we're using these resources, and looks towards a big shift in being able to use renewable sources of carbon for manufacturing. So I'm really a big supporter of this idea of biology being this great manufacturing technology. And certainly a lot of the people that we spoke to in China, which is the world's manufacturing hub at the moment, were very interested in this new technology and how they're going to be using it. And China announced at that meeting over $2 billion of investment over the next 5 years into synthetic biology research at Chinese universities. So there's definitely a huge amount of interest there.
John Cumbers, founder of SynBioBeta. John, thanks for your time today.
Thank you very much. I appreciate it.
Thanks for listening. The Bio Report is a production of the Levine Media Group. To automatically download this podcast each week, subscribe to our RSS feed or through iTunes or other podcast manager. To join our mailing list, go to levinemediagroup.com. We'd love to hear from you. If you want to drop us a line or are interested in sponsoring this podcast, send an email to danny@levinemediagroup.com. Special thanks to Jonah Levine, who composed our theme music, and the Jonah Levine Collective, which performs it.